Hello and welcome to this video on the ICND2 series. In this video, we're going to be looking at first hop redundancy protocols. So we're going to look at FHRPs, and we're going to look at the three first hop redundancy protocols that we have, which are HSRP, VRRP, and GLBP. So let's get started. So what is FHRP? FHRP means first hop redundancy protocol, and it's a protocol that is used to achieve redundancy in a default gateway. So for instance, let's look at this network. We have this device here, and normally this device can have only one default gateway. But what happens when the default gateway goes down? We have to replace the default gateway, and that's called cold standby. Another option we have is to actually have two default gateways running so that one can take over when the other one goes down. And that's the concept of first hop redundancy protocol. So we have two kinds of first hop redundancy protocols. We have to call it the hot standby router protocol, the virtual router redundancy protocol, and the gateway load balancing protocol. We're going to look at these three protocols in more details, but we're going to just talk about a few things that are common to all the three FHRPs. First thing is the addressing. Now with this device, we can only have one default gateway, but to achieve redundancy, we need to have at least two devices. We can actually have more than two devices in one FHRP group. So the question here is, which IP address are we going to give this devices as a default gateway? Is it going to be router 1's IP address or router 2's IP address? And the answer is none of them. But what we're going to do is actually create what's called a virtual IP address. So for instance, if the IP address of this router is 192.168.1.2, and the address of router 2 is 192.168.1.3, what we're going to have is a virtual IP address, maybe 192.168.1.1. And that's the IP address that's going to be assigned as a default gateway of this device. So how is this going to work? If this device wants to reach its default gateway, it's going to send an ARP message for the IP address of this device. And we know what ARP does. It converts from IP address to MAC addresses. So the second question would be, which MAC address are we going to respond with? So it's going to be router 1's MAC address, router 2's MAC address, and again, it's none of them. It's going to be a virtual MAC address. So these three protocols have their own scheme for defining their virtual MAC addresses, and that's the MAC address that we fed to the clients. And depending on which device is active at that time, that's the device that's going to be listening for the MAC address. And that's the device that's going to be using that MAC address. So for instance, if router 1 is active at a point, router 1 would be listening for 192.168.1.1. It's also going to be using the virtual MAC address to communicate with the devices on the network. So how does failover happen? Router 2 can take over from router 1 in two scenarios. The first one is if router 1 goes down completely. And the way router 2 would know is what's called hello timers. So we have hello timers, and router 2 would be listening for hellos from router 1, and router 1 would also be listening to R2. And if the hellos are not received for a particular period of time, then the device is determined to be dead. So we can say that router 1 is dead after 3 hellos and not received. And so router 2 would take over. And second scenario where router 2 takes over is when it has a higher priority. So normally for router 1 to become the active, it would have a greater priority. So for instance, router 1's priority maybe 110, and router 2's priority may like 100. So router 1 would be the default active router, but depending on the configuration, we can bring down router 1's priority to say 90, and then router 2's priority would be higher, and then router 2 can take over. But because router 1 is not dead, they actually have to configure router 2 to preempt router 1. So there's something called preemption that happens. So the way preemption works is that if the active router that has a higher priority suddenly loses some of its priority and goes to a lower priority, the standby router that has the higher priority can preempt the active router and become the active router. So that's how preemption works. And we're going to look at that in more detail when we look at the individual protocols. And in case where preemption can occur is if this router is configured to track the link to the ISP, for instance. So you can say that if this link is fast Ethernet 0/0, that if this link goes down, you should reduce its priority by 20. So for instance, so once this link goes down, even though the router itself is not down, as long as the link to the ISP is down, its priority is going to be reduced to 90, and the second router would preempt it, and it's going to become the active router. And the process of monitoring a link and monitoring a particular attribute is what's called tracking in FHRP. So we can track a link, we can track the reachability of an IP address. You can even do advanced things with IP SLA and track different SLA features, but that's beyond the scope of the CCNA syllabus. So now what we're going to do is we're going to look at the three protocols in detail. So what is HSRP? HSRP stands for Hot Standby Router Protocol. It's a Cisco proprietary protocol, meaning it can only work on Cisco devices. It's an active standby protocol in the sense that in HSRP, you can only have one active router at a time, and all the other routers will be standby. So whether it's a group of 2 or 5 routers, as long as they're using HSRP, only one of them can be active at the same time in the same group. So for instance, if router 1 is active here, then router 2 is going to be on standby. Until router 1 goes down, the router 2 is not going to become active. And the way to select the router that's going to be active is what would determine which one's going to be active is using priority. So for instance, the active router is going to have a higher priority than the backup router of what's called the standby router. Now, in default priority is 100. So by default, when you configure HSRP, if you don't set the priority will be assumed to be 100. So if you want a router to become the active router, you have to set the priority to something greater than 100. Now, this is different from spanning tree because the spanning tree, the lower priority is preferred. But in HSRP, the higher priority is preferred, and default is 100. Now, HSRP is a virtual IP address like we discussed before. So what happens is that if you have, for instance, 192.168.1.2 and 192.168.1.3, we actually have to create another IP address to be the standby IP address, which would be the group IP address for both routers. It can be any IP address in the subnet, so you can have like 192.168.1.254, for instance, but whatever the IP address is set, that's going to be the IP address that you would assign to the clients as default gateway. So if you're configuring DHCP, for instance, that's going to be the IP address you are going to set as default router. So if you're configuring DHCP, for instance, that's going to be the IP address that you would set as default router. Now, the virtual MAC address for HSRP actually has a format 0000.0C07 and ACXX, where XX is a group number. So what this means is that we have HSRP group 1. The virtual MAC address is going to be 0000.0C07.AC01. If we have HSRP group 99, the virtual MAC address is going to be 0000.0C07.AC99. So that's how HSRP generates its virtual MAC address. HSRP uses hello timers as 3 seconds and hold timers as 10 seconds. What that means is that if no hello is received from R1 in 10 seconds, then R2 assumes that R1 is dead and will become the active router. So that's one way for R2 to become the active router. Second way for R2 to become the active router is that the priority of R1 goes below the priority of R2. And that can happen if we track one of the interfaces or one of the attributes of R1. So for instance, if we track this interface, then we can reduce the priority by, say, 50. So the original priority was 120, and R2 is using the default, which is 100. Then fast Ethernet 0/0 goes down, it's going to go down by 50. So the new priority will be 70. Then R2 will have a higher priority because it's using the default, which is 100. And so if preemption is configured on R2, R2 becomes the active while R1 becomes standby. So that's how HSRP works. Now let's move on to VRRP. And VRRP is just like HSRP, except for 3 differences. The first difference is that there's not Cisco proprietary, so you can use VRRP between Cisco and non-Cisco devices. The second major difference is that the MAC address of VRRP is generated using this scheme, where XX is the group number 2. So we have 0005E0001XX. So if we're having VRRP group 20, for instance, then the virtual MAC address is going to be 0005E000120 as the virtual MAC address. And the third major difference between VRRP and HSRP is that VRRP has a hello timer of 1 second and hold timer of 3 seconds. So by default, VRRP is faster than HSRP. We can always configure the hello timers and the hold timers, so that's not really a big difference. But if you use the default timers, then VRRP will be faster than HSRP in the sense that it would take HSRP 10 seconds to know that a router is down, but with VRRP, it only takes 3 seconds. You can also do track and decrement priority with VRRP, and the default priority is still 100, so it's pretty much the same, except you can now use it for non-Cisco devices. So VRRP is just the industry version of HSRP. Now let's look at the third redundancy protocol, which is GLBP. Now GLBP stands for Gateway Load Balancing Protocol. It's also a Cisco proprietary protocol, so it can only be used on Cisco devices. But GLP is different from HSRP and VRRP because GLBP actually uses what is called active-active redundancy. What that means is that it doesn't just do active and standby, it actually load balances traffic between the two devices. So you have failover happening, but the two devices are being used at the same time. So think of it like per VLAN spanning tree protocol, where you can have different root bridges and use all the links. So the same thing here. You have these two devices acting as redundant devices, backup for each other, but they are both being used at the same time. So some of the traffic will be sent through R1, some of the other traffic will be sent through R2. But if R1 goes down, then all the traffic would be sent through R2. And if R2 goes down, all the traffic will be sent through R1. So how does it work? We have something that's called an active virtual gateway. And the active virtual gateway is the manager of the GLBP process. So what really happens is that the AVG coordinates and is the one that responds to the virtual IP address. So for instance, if we have 192.168.1.2 here, and 192.168.1.1, and the virtual IP is 192.168.1.254. So that would be the default gateways to assign to the clients. Now, when the client asks for 192.168.1.254, the AVG, which is router 1 in this case, is going to actually reply with a virtual MAC address. But instead of having just one virtual MAC address like in HSRP and VRRP, with GLBP, we actually have more than one virtual MAC address. In fact, we have as many virtual MAC addresses as many routers as we have on the network. So what AVG does is that it assigns one virtual MAC address to every router, and that's in the group. So in this case, we just have two routers in the group, but even if we have more than two routers, each of the routers would have a virtual MAC address. So when it receives the first ARP request from the client, it's going to respond with the first virtual MAC address. And then when it receives another ARP request, it's going to respond with another virtual MAC address, which is for the second router in the group. So each of the routers are actually going to be forwarding. So they're all called active virtual forwarders. So with GLBP, we have one AVG and many AVFs. So the active virtual gateway just coordinates everything and responds to the ARP request, but responds with different virtual MAC addresses for each of the AVFs. So how does backup occur? First thing you need to know is that we still have the hello timer and the hold timers, so we can still know when the router goes down. And the router with the highest priority is still the AVG. So the router that has the highest priority will be the active virtual gateway. What happens if like an active virtual forwarder goes down? What really happens is that when the active virtual forwarder goes down, the router with the next highest priority, which is usually the AVG, would take over. And when I say take over, what I mean is that the router is going to start responding to the AVS MAC address. So for instance, if this router goes down and it had a virtual MAC address of 2222.2222.2222, so what's going to happen is that when the device tries to send traffic to this MAC address, 2222.2222.2222, router 1 is actually going to take that traffic and it's going to forward that traffic. So the device does not even know that this MAC address has gone down. And this process is what's called redirection. Well, it's actually redirecting the traffic that's supposed to be meant for the AVF through itself. And while it's doing this, it actually counts down the redirect time, which is 10 minutes. So after 10 minutes, it knows that the router is not coming back up. And what it's going to do is that it's going to stop giving out this MAC address. So when devices ask for a MAC address, it's only going to be using the MAC address on the remaining AVFs, but it's not going to use the MAC address of the AVF that's gone down anymore. So that's how the failover works. And that's just like HSRP and VRRP, we can actually track interfaces and decrement priorities so that some other device can fail over, whether for the AVG or for the AVF. So In this video, we started by looking at what FHRPs are. We looked at the first three protocols. So we looked at HSRP, which is a hot standby router protocol. We also looked at VRRP, the virtual router redundancy protocol. And we looked at GLBP, the gateway load balancing protocol. And the next video we're going to do is we're going to go to command line and see how we configure these protocols and how these protocols work. Thank you very much for watching. Hello and welcome to this video on the IC&D2 series. In this video, we're going to be looking at configuring HSRP and VRRP. So we're going to be spending most of the time on the command line, and we're going to be using this simple network topology. So here we have R1 and R2 connected as the gateways, and the network here is the 192.168.2.0/24 network. Our test host, which is a laptop, is .19. Router 1 is .2, and router 2 is .3. On the outside, we have fast Ethernet 0/1 of router 1 and fast Ethernet 0/1 of router 2, and they're connected to our ISP, which is just a cloud of routers that we have, and our test IP address would be 8.8.8.8. And what we want to do is to configure HSRP and VRRP using the group address 192.168.2.1. And that's going to be the default gateway assigned to the clients. So let's get started. So we are on router 1 right now. We're just going to show IP interface brief. So here we are. We can see we just have three interfaces, the 192.168.2.2 and the 123.123.123.1, which connects to the outside. So what we want to do is to try to ping. So we're going to ping 192.168.2.3, which is router 2, and we can ping. We're also going to try to ping 8.8.8.8. And yes, we can ping it, so we are fine. So we want to configure HSRP right now. So what we're going to do is go under the interface, so conf T, we go under the interface and say interface fast Ethernet 0/0, which is the interface that's connected to the clients. If we do show run interface fast Ethernet 0/0, and that's all that is there, the speed and the duplex. So we're going to configure HSRP, and the keyword to use here is standby. So we're going to say standby. Now the next thing is to give a good number, so we can have the next thing is to give a good number, so we can have from 0 to 255. So I'm just going to use standby 1. And next thing is to put the standby IP address, which is 192.168.2.1. Now, the next thing we have to set is a priority. So we're going to say standby 1. And if you want router 1 to be the active router, we're going to make its priority 110. And right now, it said that router 1 has gone from standby to active, but the real truth is that router 2 has not been configured, so it really doesn't matter. Now, there are many other features we can use, like authentication, configuring the virtual MAC address, setting the timers. Like, for instance, if you want to change it from default, which is 3 and 10, we can use standby timers, standby 1 timers, standby 1 timers. And of course, we can set the hello interval as whatever we want. And notice here that we can actually make the hello timer in milliseconds to even make it a lot faster than VRRP. So VRRP is only faster than HSRP by default, but it's not always faster because you can switch the timers. But right now, we're just going to leave it at default, which is 3 and 10. But right now, the config is fine, so we can just do show run interface fast Ethernet 0/0, and that's all we need to configure HSRP. If we go over to R2, we're in R2 now, we're going to do the same thing. So we're going to go into the interface and say conf T, interface fast Ethernet 0/0. We're going to say standby. The group number has to be the same for them to be the same group. So it has to be standby 1. And then we're going to give the same virtual IP, which is 192.168.2.1. And we're going to leave the priority as default. So once we do that, so right now, we just need to configure the default gateway for the clients as 192.168.2.1. That's all. And HSRP will be working. And if one router goes down, the other router can take over. So we're back on the client now. And we do an IP config. We would see that the IP address is 192.168.2.19. And the default gateway is set as 192.168.2.1, which is the virtual IP address for the HSRP group. So let's try to ping 8.8.8.8. And now we can reach it. Now we do an ARP, and we can see that 192.168.2.1 is being dynamically resolved to 00.00/0C/07/AC/01. And what this means is that this is the virtual MAC address of the HSRP group. So first it says what we're going to do is put a continuous ping. So we're going to ping 8.8.8.8-T, and then we're going to try to shut down the primary interface for the HSRP group and see if it fails over. So let's ping. So I'm going to remove the cable connecting fast Ethernet 0/0 from the network. And if you can see, we begin to get timeout. So let's see how many timeouts we get. We get 2 timeouts, and then we get replies again. And that means that the failover has taken place. So we can't receive right now. The R1, we can't see any logs. If we go to R2, we can see that R2 has changed from standby to active. And that's because HSRP has failed over to R2. If we check our ARP table right now, we can see that there's no difference in the ARP table. You see 192.168.2.1, and the virtual MAC address is still the same. So the device has no clue that anything has gone on. But if we show standby on R2, do show standby, we can see that the state is now active, and it's now the one in charge of the virtual MAC address. Now, it says standby router is unknown because it has no clue where R1 is, because R1 has lost its connection to the network. So I'm just going to put R1 back and see. Now, the R1 is back, it's become the active again, and R2 has gone back to standby. So if we want to go to R1 and do show standby, we can see that the active router is local router, and the standby router is 192.168.2.3. Now, if we go back to our network, in the example that we looked at right now, we actually brought down this link because the hello packets are being sent out this link. Router 2 thinks that the router has gone down because it doesn't receive any more hello packets. And so it becomes the active router. And when it comes back up, then it takes over as the active router again. But what if an uplink fails? What if it's this fast Ethernet 0/1 that fails? If R1 is the active router and fast Ethernet 0/1 fails, even though R1 will still be sending hellos, it'll still be in the HSRP group, it's useless because the client cannot go through R1 to get to the ISP anymore. So what we need to do is to make sure that if this link goes down, that this router starts becoming the active router. And the way to do that is to track it. So we're going to track this link. And the way we're going to track it is that if this link goes down, we're going to decrement the priority. So the priority goes from earlier 110. And if it goes down, we're going to decrement the priority by 40. So that the priority will become 70. And then R2's priority, which is 100, will be greater. And because of that, it's going to become the active. But in this case, we have to configure preemption on R2. So we're just going to go to R1 and R2 and configure preemption right now. So in R1, I'm just going to say standby 1 preempt. And we're going to do the same thing on R2. So standby 1 preempt. And then we're going to go to R1 to configure our track. So we're going to say standby 1. Standby 1. I can't spell. Standby. And this is track command. So we're going to say standby 1 track. And we can track any of the interfaces. So we're just going to say you should track fast Ethernet 0/1 interface. And then we have the decrement value. So we can just decrement it by 40. In this case, what happens is that if the line protocol on fast Ethernet 0/1 goes down, it's going to decrement the priority of R1 by 40. So R1's priority will become less than that of R2. And because of that, R2 is going to become the active router. So again, we're going to turn on our extended ping. And I'm going to go to R1 and shut down the interface. So interface fast Ethernet 0/1. I'm going to shut it down. And we can see that immediately that happens. The first thing we can see is that the tracking state went to down, and that's because the line protocol changed to down, and R1 itself went from active to speak. And we can see that on R2, it went from standby to active. So R2 is now the active one. And if we check our pings, we can see we only lost one ping. So it's a lot faster because it's tracking it. And that's how tracking works. So if we do show standby right now, on R2, we're going to see that R2 is the active router and that preemption is enabled, and that's why it works. And of course, if we do show standby on R1, standby, we're going to see that the track is down. It says that the track interface, fast Ethernet 0/1, and the state is down, so it's 40. And if we check the priority, we're going to see that the priority is 70, even though we configured it to be 110. And that's because the track has decremented it by 40. So that's how HSRP tracking works. Now, we bring back up the interface and we say no shut. Now, if we go to R1 and bring up the interface and we say no shut, we can see that immediately the tracking state came back to up and it came back to active. It went from standby to active, and router 2 went back to standby. So that's just how to configure HSRP. We just need to configure the standby IP address. Make sure that the standby group numbers are the same, configure the standby priorities, configure preemption if you want to, and configure tracking. Now what we're going to do briefly is to do exactly the same thing for VRRP. So VRRP, we're going to configure VRRP on router 1 and router 2, and we're going to do exactly the same thing, except that we're going to make router 2 the active one this time. So router 2 is going to have VRRP priority of 110, while router 1 is going to have VRRP priority of 100. And we're going to track on router 2. We're going to track its interface, and we're going to bring it down by 40 if the interface goes down. So let's get started. So on router 1, and what I'm first going to do is take off all the HSRP commands. So I'm going to say no standby 1, and it's going to take off all the HSRP commands. I'm going to do the same thing on router 2. So HSRP has been enabled. So we're going to configure VRRP now. And the command to use here is, instead of using standby, is to use VRRP. And the same thing, so VRRP, give it a number. We're going to say IP address should be 192.168.2.1. Same thing. In this case, we want router 2 to be the active one. We're going to leave router 1 as default. And then we're going to say VRRP 1 preempt. And that's all. And then we're going to go to router 2. As I've disabled HSRP on router 2 too. So we're just going to configure VRRP. So we're going to say VRRP 1. The IP address should be 192.168.2.1. VRRP 1. The priority should be 110. Now, if you notice, even without making priority 110, it became the master. The reason is because for HSRP and VRRP, if the priorities are tied, that means they have the same priority, the default priority of 100, then the router with the highest IP address is going to become the master or active in terms of HSRP. So if the priorities are tied, then the IP address is used to break the tie and the router with the highest IP is chosen, but we're going to set the priority as 110. Now, we're going to configure preempt too, so VRRP1 preempt, and then we're going to configure tracking, so VRRP1 track, and in the case of HSRP, we could track the interface directly. But in VRRP, we have to use what's called a tracked object. So we're going to call the object 1. And we're going to say decrement 40. So what we need to do right now is to configure the tracked object. And we have to do that from the config mode. So we're going to say track 1, since we call the object 1. And what do we want to track? We want to track an interface, and the interface is fast Ethernet 0/1. We have to decide what parameter of the interface we want to track. However, we're going to track is the line protocol. Now, if we show VRRP right now, we do show VRRP. R2 should be the master. So the master router is 192.168.2.3, which is a local router, and the priority is 110. While HSRP uses active and standby routers, VRRP uses master and backup router, but it's exactly the same thing. So what we're going to do right now is turn on our extended ping from the clients. So we're going to go to the clients, and the ping is still running. So we're going to shut down the interface fast Ethernet 0/1 of R2. And that has connections to the ISP. So we're going to say shut down interface fast Ethernet 0/1 shut down. And the moment we shut it down, we're going to see request timeout, and it comes back immediately. That's because on R2, we can see that first the track goes down, and then the VRRP, we can see that goes from being master to backup. And when we go to R1, we can see that R1 has gone from backup to master. So if we do show VRRP on R1, we can see that it's the master and its priority is 100. But on R2, if we do show VRRP, we can see that even though the priority is 70, the configured is 110. And that's tracking an object. And because the track is down, it decremented the priority by 40. So we bring it back up. We say interface fast Ethernet 0/1 and no shutdown. It's going to come back up to the master. And we're not even going to lose a ping. So everything is still going to be fine here. So that's how HSRP and VRRP work. So in this video, we have been able to configure the hot standby router protocol and the virtual router redundancy protocol, and been able to configure priorities, and able to configure preemption, and have been able to configure tracking for both protocols. Thank you very much for watching. Hello and welcome to this video on the ICND2 series. In this video, we're going to be looking at GLBP. So we're going to continue from right where we stopped, configuring HSRP and VRRP on the last video. We're going to configure GLBP. So let's get started. We'll work on router 1 now. And what we're going to do is to turn off VRRP. So we're going to go into the interface, VRRP, and remove VRRP. And the ways to do that is to go into the interface. We say interface, fast Ethernet 0/0. Then we say no VRRP1. And we're going to do the same thing on R2. So we're going to go to R2. So now we're going to go to the interface, and I'm going to say no VRRP1. Now I'm going to configure GLBP. And it's almost the same way we configure HSRP. So we're in R1 now. What we're going to do is say GLBP 1. We're going to give it an IP address 192.168.2.1. Next thing we're going to need to do is select the priority. So one needs to be AVG. So we're going to say GLBP1 priority should be 110. And really that's how it's configured. We can go to router 2 and configure GLBP now. So we say interface fast Ethernet 0/0. And would say GLBP1 IP address should be 192.168.2.1. And we're going to leave the priority as default. Now we showed GLBP on router 1, so we do show GLBP. First thing we can see is for fast Ethernet 0/0 is in group 1 and state is active. That means that this router is AVG. And we can also see here that active is local. Right now it says standby is unknown, but if we do show GLBP again, we can find the standby because router 2 has come up now. So active is local and standby is router 2. We can also see that the priority is 110, and that's a priority that we configured. Now, if we go there, we can see that for forwarder 1, the state is active, and this is the virtual MAC address. But the real MAC address is this, and the redirection is enabled. If we go down to forwarder 2, we can see that the state is listen, which means that it's not the active virtual forwarder for the second forwarder. So we have two AVFs. Router 1 is active for the first AVF, while router 2 is active for the second AVF. So we go to router 2. We can even see from the log that is in group 1, but the forwarder 2 state is changed to active, means the active virtual forwarder for the second forwarder. So if we do show GLBP, we can see that the state is standby for the group. For forwarder 1, the state is listen. But if we go down to forwarder 2, the state is active. Now this is very important to know how load balancing works. And another thing we can do is to go see that if we go up, we can see that the load balancing is round robin method. What the round robin method means is that for every ARP request, the AVG is going to send a different AVF. So what's going to happen for the first ARP request, the AVG is going to send the MAC address of AVF1. And for the second ARP request, the AVG is going to send the MAC address of AVF2. So in this case, for the first ARP request, the AVG is going to send virtual MAC address of router 1. And for the second ARP request, the AVG is going to send virtual MAC address of router 2. That's how load balancing works. Now, we can actually change the way load balancing works. For instance, we can go to GLBP and say GLBP1 and configure load balancing and say instead of round robin, the round one host dependent, what this means is that for every host, it's going to have one virtual forwarder. So once it sends a MAC address, that's going to be the virtual router that a MAC address would continue to use. And then the next host, we use the next MAC address. Now this is a little different from round robin in the sense that for round robin, for every ARP request, it changes a MAC address. So if I have one host, I could just try to ping, for instance, let's take an example. So right now, we're on the host. We're going to try to ping 88.8.8.8, so 8.8.8.8, and we can see that the pings are going through. If we do ARP, we're going to see that 192.168.2.1 is translated into this MAC address, 0007B4000102. Actually, that's the MAC address of R2. So if we go to R2, we can see that the MAC address is 0007B4000102. What happens if we clear the ARP? So I had to run as administrator in order to clear the ARP. So let's just clear the ARP. So we're going to say ARP *-D and clear the ARP. So we can try to ping 8.8.8.8 again. We can go through, but if we check the ARP table now, we can see that the MAC address has changed to router 1's MAC address. It ends with 0101. So we can see that there is load balancing on the round robin basis. Now, if we want to change it to host dependent, so for instance, if we go to router 1 and we say GLBP1, load balancing, use a question mark, and we want to use host dependent. So we're going to change our router 2 too. So we're going to say GLBP1, host dependent, load balancing, host dependent. And if we come back to the client and then we try to ping, we check the ARP. Right now it's router 2. Now let's try to clear the ARP again and say ARP *-D and then try to ping again and then check the ARP. We can see that it's still router 2. It's no longer changing the MAC address, and that's because the load balancing is now host dependent. So anytime that was going to use router 1's MAC address is if another host comes in and requests for a MAC address. So the last kind of load balancing feature we have is the weighted one. And for the weighted load balancing, what it really means is that we have to configure weight on each of the forwarders, and based on the weights that we've configured, that's what the AVG will use to load balance traffic between the MAC addresses. So if one has the weight of 100 and the other one has the weight of 50, that means that for every 2 ARP requests, it's going to send the first MAC address, and then the third one will go to the other one because it's in the ratio to 2:1. Besides load balancing, weighting is also used to determine the failover for the AVFs. So if we want to configure a weight on router 1 right now, so we're going to go into GLBP and say GLBP1. We're going to say weighting, and then we're going to have a weighting value. So for instance, we're going to say 100. We're going to have an upper and lower threshold. So we can say that our upper threshold is 90 and our lower threshold is 70. So we have to define them separately. So lower threshold is 70. Now, what weighting really means is that if we have the weighting to be defined as 100 and the upper threshold is 90 and the lower is 70, what it means is that as long as the weight of this router, this is 100, router 1 will continue to be the AVF for that forwarding group. But when the weight goes below the lower threshold, which means it goes below 70, it's going to stop being the AVF. And then for it to come back and become the AVF, it has to go above 90. So this might not make sense right now, but what it means is that if you have a router 1, and for instance, it's connected to more than one link, or you're tracking more than one particular attribute, we have, for instance, fast Ethernet 0/1 and serial 0/1. Now we can track both of them, and we can say that for each track, we're going to decrement 20. So what this means is that if the first interface goes down, the weighting will go from 100 to 80. And because it's still 80, it hasn't gone below the lower threshold. It's still going to be the AVF. But if the second interface goes down and decrements another 20, it's going to go down to 60. And once that happens, it's going to be lower than the lower threshold. And so router 1 will stop being AVF. And for router 1 to go back to being the AVF, if we bring up one interface, it's going to back up to 80, but because it's not the upper threshold, you have to bring up both interfaces for router 1 become the AVF again. So you have to take it to something greater than 90, and that's how it works. So that's how GLBP weighting works. So for instance, if we go back to R1, we've configured the weighting for the upper threshold to be 90 and the lower threshold to be 70. So we can just configure a track. So we're going to say GLBP1 track. So we're going to say GLBP1 weighting, then track. And we're going to say if you track object 1, for instance, and decrement by 20. But because we have only one object, we're going to decrement by 40. So they can go below the lower threshold. And then we're going to define our track. So we're going to exit and go to the config mode and say track 1. You should track interface fast Ethernet 0/1. And you could track line protocol. And then we would exit. So if we go under the interface and we say interface fast Ethernet 0/1 and we shut it down, for instance, we're going to see that the tracking state has gone down. And because of that, the weighting would have reduced. So if we do show GLBP, we can see that the weighting is now 60. We can see that for the forwarding state, it's gone from active to listen. And that's because the weight has dropped below the lower threshold, which is 70. So now there's 60. It can no longer become the active virtual forwarder. So we do show GLBP again. We can see that the router 1 is still the AVG for the group, but the state is still active, but it's no longer the AVF. And that's because the weight has been manipulated. So the AVG is controlled by the priority, while the AVF is controlled by weights. So in this video, we looked at how to configure GLBP, the AVGs and the AVFs, and how we can failover between the AVGs and the AVFs. Thank you very much for watching.